whereas the charge, the force carrier, the gauge bosons, they have integer spin. And by the way, they are called bosons. Of course, everybody in India must know about Boson, who worked about 100 years ago together with Einstein on very fundamental issues of particle physics, And the last piece, really, of this landscape is the Higgs boson, which is very special. It's a scalar particle because its spin is 0. On the next slide, I just give you a short hint to the history of the Standard Model and of the big question which was solved by the gentlemen like Peter Higgs, Robert Prout, François Englert, and some others. This was a question coming up in the 60s. Why do elementary particles have a mass? In particular, also, why are these masses so different? And why is, for example, the photon 0 mass, whereas the WZ, the gauge bosons, have a very large mass? In fact, the gauge theory would have predicted that predicts that all elementary particles that are point-like and have no internal structure, and as a consequence, they would be massless. But the series I just mentioned, they introduced in 1964 the concept of a spontaneously breaking of this symmetry, in particular, the breaking of the symmetry between the massless photon and the heavy W and Z bosons. It's a gauge theory, and the potential is sketched here. You have even the mathematical formula. You can see that actually the zero point would be on top of this little mountain of the potential, and it's, one calls it spontaneously broken because the lowest level is not at this 0 point, but indicated a little bit lower by this ball, and one sometimes also calls this potential like a Mexican hat. Now, what are the consequences? Well, it predicted that there should be a field which is present all over the vacuum, and the bosons, they can acquire mass, and the fermions by interacting with this field. And one can also excite this field, and then the excitation of this field would materialize in a resonance in the Higgs boson. So that was the conjecture in the 1960s, and we have been trying to prove this by indeed finding the Higgs boson. Just a side remark, which will also be useful, is that, of course, sometimes one reads in newspapers or so, well, the Higgs boson is responsible for all the mass. This is not really true. It's responsible for the mass of the elementary constituents of the quarks or the W and Z, but most of the mass actually, which we encounter in the proton or in the antiproton, in the neutrons, comes from the binding energy of these constituents. It's just the famous Einstein energy equals mc square, which is at work here. So only about 1% actually of the mass is directly a consequence of the Higgs field. I just wanted to say this because that's sometimes wrongly transmitted, let's say, in the media. Okay, so here we see the proton, and you know this, I assume, from your lectures, are composite objects, in particular between up and down quarks, held together by gluons. And in fact, when we make collisions between proton beams, as we do in the LHC, it's not really the protons as a whole which interact, but are constituents, either quarks or, as it is sketched here in this cartoon, for example, two gluons, they can interaction which will produce, for example, a Higgs boson, which in turn can decay, for example, in a W pair or in a Z pair. So, okay, let me now go to a bit to the history of machines, and just to say that the LHC is really the last step in a long history of hadron colliders. Hadron colliders where one tried to reach higher and higher energies such that one can produce more and more massive particles. So the first of these hadron colliders was the Cern intersecting storage ring in the 70s. I was just a postdoc. Well, I made my PhD there, and then postdoc, I worked on this machine. And it shows you here the principle of particle accelerators and colliders. So there is a synchrotron which accelerates particles, and then they were filled in two rings. Actually, the circumference of this ring is about 1 kilometer, the ISR at that time. And these rings, well, one fills them such the particle goes clockwise or anti-clockwise, and then at some points they are brought into collisions. And this is showing you a picture of such a collision point. Here you see the two beam pipes, and inside this detector, they collided, and then we had instruments around it to see the particles which emerge from these collisions. And that's a picture of me, by the way, many, many years ago. So that was the first collider, and then the energy was only up to about 60 GeV, 60 times, roughly speaking, the mass of the proton. So not very heavy particles could be produced. And in order to find the W and the Z boson, we already knew at some point that you need to have higher energies because the mass were expected to be in the range of, roughly speaking, 100 times the mass of the proton. So the way this could be achieved was with an accelerator, which was already existing just to accelerate particles, protons. This is a ring of about 7 kilometers. And then Carlo Rubbia, who got the Nobel Prize afterwards, had the genius idea that if you put in the same ring in one direction protons, and then actually you could accelerate and have antiprotons in the other ring, you could bring them to collisions. And indeed, as this machine had something like 400 GeV energy, you would have 400 GeV colliding with 400 GeV antiprotons. So you would have a lot of energy available. And that was then the Cern P/P collider. Of course, here you see actually a picture of this collider. As I said, it's about 7 kilometers in circumference. The only problem was, of course, to produce a lot of antiprotons and to inject them in the other direction. This was done by special machines well, antiproton accumulator and antiproton storage ring. These were smaller machines, but it was already quite a complex thing. And also the detectors grew larger. If you remember the first one I showed you from the ISR, this is the famous UA1 detector. There was another one called UA2, which was actually used to detect the W and the Z boson. And just to show you two pictures of the 1980s, this is a picture what happens in a proton-antiproton collision where actually an electron was produced of very high momentum, 40 GeV, and only low energy tracks around it, not balanced by anything. So one could deduce that there must have been an undetected neutrino, neutral particle, which does not interact much with matter on the other side, and that was a clear signal for the W. Even much cleaner was the signal for a Z particle, which I show here a display of the energy deposit in a way on a cylinder around this interaction point. And you see two electromagnetic spikes of energy, because this is the cylinder is then unfolded on a plane. They are here 180 degrees in phi opposite to each other. And indeed, they have roughly the energy deposited in the electron and the positron corresponded to a particle of roughly 90 GeV that decayed in E plus E minus. And indeed, this was the signal. Just if you look on the invariant mass scale, as we say them, we found an accumulation of events around 90 GeV. Just notice how few events there were. This was in UA1, just 4 events. In our experiment, UA2, we had a bit lucky fluctuations. We have something like 8 events here. Okay, then, well, this collider was working for almost 10 years. And at the end, we had quite a lot of Ws, for example, and could also measure very precisely already the mass of the W, about 80 GeV. The mass of the Z was about 92 GeV. And now something very special of the standard model, actually knowing the W and the Z mass, one could already predict what should be the mass of the last quark, which was not yet discovered at that time, the top quark. And it turned out to be, this prediction to be very high, 160 GeV, well, with big errors, because there were also errors on these measurements. But this way, it's clear that one needed even a higher energy collider to find the top quark. And this higher energy collider came into operation in the early 90s at the near Chicago, and it's called the Tevatron. And it provided, it was again a proton-antiproton collider. It provided collision at 2 TeV, 2 teravolt. That means 2000 GeV. So ISR was 60 GeV. Cern P/P collider was typically 600 GeV. This now 2000 GeV. And this indeed allowed, with sophisticated instruments, which I just show here 2 pictures of, there were 2 detectors, allowed actually to produce the heaviest quark, which was predicted, as I said, to be roughly 160 GeV. Well, it turned out to be 172.5 GeV. It was produced by a pair, a top and an anti-top quark, which immediately decay into a W and the B quark, and then the W, for example, decays in an electron and a neutrino, as I mentioned, for the discovery of the W, typically. It can also similarly decay into a muon and a neutrino. And it was in 95 that in a packed auditorium in Batavia, near Chicago, this announcement was made. So at that point, of course, everybody was thinking the standard model must be really correct, and there must be somewhere this last missing link, the Higgs boson. This shows you just some pictures of how these events, these collisions, were reconstructed in the two detectors. Again, the time is not, I have not enough time to explain this to you, but there are typical signatures, as I said. For example, here, the B quark, that has the property to fly a few fraction of a millimeter before it decays, so it has a quite finite lifetime. And if you look here, you see actually indeed there are some flight passes before the B quark then also decays. And well, in the beginning, that's what they saw, some accumulation of candidate events, typically at the predicted mass of 160, well, as I said, a bit more, 170 or so. Okay, that was the Fermi-Lab collider, and now let us go really to the main matter, namely the LHC. The LHC is housed in a 27-kilometer tunnel, typically about 100 meters underground, near the Geneva airport. So sometimes as a joke, we say here we accelerate airplanes and here we accelerate particles. And it's a long history. Actually, the first time one was thinking about the LHC, that goes back into the late 70s. A lot of credit has to be given to Professor Tsikiki, who said we should really build such a tunnel large enough that we can reach many TV's collision energy. And then it took a long time. And in fact, only in the 1980s, when we discovered the W and the Z, people, you have already seen this picture of the Z, people started to believe that in hadron collisions we can actually find very rare new heavy particles. And that was during the time when Professor Schopper was the Cern Director General. And let me also say, just for the fun, of course, I was still I was a very enthusiastic experimental particle physicist at that time, working on the UA2 experiment, that we said, well, let's go immediately and build this. And we actually thought that we could have the LHC running already in 1998. Now, just you will see a little bit later, actually it took 10 years more to build it, but it's always good to be optimistic. So the story is it's a very big and expensive machine. So it needed a lot of work to actually convince the governments who pay the CERN laboratory, that they embark into building this machine. And that's really the merit of Chris Levlin-Smith, who was at that stage then Director General. Well, first, there was not enough money, so one thought one would build it in stages, but then go and find countries outside Europe who would also contribute to this machine. You see, that's how the LHC became not only a European machine, but really a machine with a worldwide participation. In particular, also India agreed to contribute to some elements of the machine. So in '96, then the machine was really approved for construction the way we know it now. Just a short word, what are the elements of such a machine? Well, of a collider, first of all, you need dipole magnets to keep the particles on their track. And you need quadrupoles to focus the beams. Then these are magnetic elements, and they are supraconducting elements. Then you need what is called radio frequency cavities, where you accelerate the particles. The particles are not accelerated by the magnets. They are accelerated by an electromagnetic field, which is arranged such that any time, about 11,000 times per second at the speed of light, when they come through, they get a little kick. And every time they go to a higher energy. And then, of course, you need what happens at the collision. So, how the elements look like in practice. These are the main elements of the accelerator. They're supraconducting magnets. The beams here are now proton and protons, and in one tube they go into the plane here, and in the other tube they would come out of the plane. There are 1,232 such 15-meter long cryomagnets, and that's the biggest part really of the machine, the most expensive one, just to give you an idea. Now, how is it possible? So here you see just how the magnetic field is arranged. You want one beam going in that direction, the other beam in the other direction. So of course the magnetic field has to be opposite in the direction on the right side compared to the left side. And, these coils have to be cool because they work at actually even super liquid helium temperature, 1.9 degrees. And then is a picture of the elements where the particles are accelerated, these radio frequency. They're also supraconducting devices, so a very complex thing. And finally, near to the place where you want to have the interactions, you have to make the beams very, very dense. So you have to focalize them with well, quadrupoles, as I said. And you can see here actually, for example, these were elements also built by non-European participants, which contributed to the machine. In fact, this by Japan, KK, and by Fermilab in the United States. So it's really an accelerator where the whole community has contributed. So let us look now a bit more about collisions at the LHC. Well, we knew that the production of a Higgs particle, for example, which we can detect, would be very rare. namely only once in 10 to the 13 collisions. So obviously you need to have a lot of collisions. So you need to have many packages of protons which collide. For example, there are 10 to the 11 protons per bunch. There are 2,800 bunch in one direction, in the other direction. But they also need very sophisticated instruments, of course, to find these very rare events. Now, so we had to think about how to make the experiment. I was an experimental physicist, not a machine builder. This is mainly engineers, but we were actually proposing experiments already in '92. First ideas, there were several ideas, as you can see, several collaborations, what they want to do. Two of them, we went together, we joined forces. This is typical in these big projects that obviously we can only build very few, one or two of them. So you better join forces. And that was in 1992 that by joining forces, we established the Atlas collaboration. And that was the official birth of the project I'm talking about. So this was Atlas, a similar second big detector in parallel was proposed and at the end realized, which is CMS. I will say also a few words about CMS because that's the experiment where Indian teams are working. There are two more smaller experiments specialized for studying the B quark. It's called LHCb, or for, in particular, looking at collisions, not only of proton-protons, but also of lead nuclei. So this is more nuclear physics studies in ALICE. Atlas and CMS are really the big general purpose detectors which have jointly discovered the Higgs boson, and they have chosen very complementary configurations. One did not want to have two identical experiments because maybe one wouldn't work or so, so you want to have complementary independent detectors. And one of the big differences is the CMS experiment is based on a very big solenoid. In red is where the current goes. So you all know from lab work what is a solenoid. So the magnetic field here is along the axis. Whereas we in Atlas, we choose a different way. We wanted to make a toroid, and you will see later on how this looks like. So actually the current is in coils outside, around, and then the magnetic field is shown here like the blue. So it's just perpendicular. It's really completely different. Here a picture of the CMS experiments with the solenoid and then particle detectors for photons, electrons, for example, electromagnetic calorimeter inside with crystals, tracking detectors at the very inside, and here is where the particles would collide, and then the muon outside is big. And this is just now a cut through perpendicular to the beam axis, where you see the principle, namely tracking chamber, where you see the charged particles. You measure the theta, the bending, which is inversely proportional to the momentum. You measure the energy in electromagnetic and hadronic calorimeters, and then outside you measure really the muons, the only particles which go really through all this matter of the detector. picture, it's a big solenoid. You see it here being assembled. You notice the size of persons. And maybe another picture of the CMS speciality. This is the crystal calorimeter, something like 80,000 crystals, where you can actually measure with high precision the photon and electrons. And this detector was assembled on the surface and then lowered down 100 meters. Remember, I said 100 meters underground, very big pieces. And that's a picture of the CMS detector just before closing. The collisions will be inside here, and you see here nicely the different particle detectors. Okay, now I switch to Atlas, which is even bigger in size, giving you here some dimensions. It has a radius, well, about 12 meters, a length, the total length about almost 50 meters. And you see here coils of the maybe a word to the collaboration. They are very big. So there are today about 3,000 scientific authors and a lot of students. You can see 1,200 students. Well, 40 countries, many institutions. They are listed here. And very similarly, world-spanning is the collaboration for the CMS detector, which has a strong Indian participation. You see something like total, if you take everybody, engineers and everybody, something like more than 200 collaborators. Here they are, where they are in India. And in fact, you can find more about these detectors in many excellent public lectures by a very prominent Indian physicist, Archana Sharma. She works on CMS and she's also a good friend of mine. Okay, so back to Atlas. You see this detector is installed in a big cavern. Obviously it needs to be big because the detector is big, on the LHC ring. And then again, here in the center would be the collision. This shows you a picture when the cavern was made. It was a huge cavern. So this is about 40 meters and 50 meters in length. This was in 2003, just at the beginning of 2003, so 17 years ago. And maybe a few of the technical things. One of the biggest devices is this toroid magnet, which has 8 coils in the barrel. They're shown here in light blue, and they have a total of about 80 kilometers of supraconducting. So they make a big magnetic field. I will show it to you, but just to give you an idea, it's really big, of course, big engineering pieces. This is one of these 8 coils during the transport. So you can see it's big. And then when it was assembled, it took about 1 year. This is now looking in the direction of the beam. You see these 8 coils, and the magnetic field would go like that. So you also understand why it is called toroid. That was just a magnet, and then, of course, one had to fill it in with particle detectors. I will not be able to go into much detail, but just to give you a flavor, one of the main detectors, which has the same purpose as the crystals in the CMS experiment, is called a liquid argon, a cryogenic electromagnetic calorimeter, which has fine pieces of absorbers and then electric field, electrodes, and when you have electrons, they shower or photons in this device, and you measure actually the electrical signal of them. So just to show you again somehow the long path from very first prototypes. This was a little thing, just much less than a square meter, which we did in 1990. Then we developed this more and more, this device. You can see here the shape. It was kind of accordion. It was, as it was many French groups, they like to call it accordion because accordion is a popular music instrument in France. So it looks like an accordion, but of course it's not. And then there are many, maybe 32 of such modules which were built with about 200,000 electrical channels. And then they were inserted into the cryostat because liquid argon needs to be cooled to about 80 degrees Kelvin. So again, a large engineering job. Here you see it already, the calorimeter, this is this part, inserted in the cryostat, and we insert also a relatively small supraconducting solenoid inside. If you would see this very clearly, you would see this is a Japanese gentleman, and indeed this solenoid has been built in Japan and then shipped to Cern, and at Cern it was put into the detector. So there are many such details, stories to be told. For example, the hadronic calorimeter was built, actually the modules, the iron structure, very fine iron structure, then segmented with scintillated plates. This was built in Russia. And then the scintillator were inserted, 500,000 of such scintillated plates, and they are read out by what is called wavelength shifting fibers into something like 10,000 photomultipliers. Here you see the first of these modules already being put together. That was in 2004, and then lowered down into the pit. And after some years, 2007, this shows you now again the toroid, but already also instrumented with muon chambers, end caps, and an idea of the complexity. What is not yet inserted here is the high tech silicon detectors in order to intercept all the charge tracks just after the collision, which would happen here. So inside there is a pixel detector with something like 80 million channels, and then silicon detectors. You see here some pictures of this high-tech detector and just the insertion of the silicon detector, which happened in 2007. Finally, the overall tracking detector went inside the already assembled outer part of the Atlas detector. So just to let you know, this construction phase and assembly went from 2004 to about 2008. This also gives you an idea about the outer detectors, the muon chambers, which again, several hundreds of these detectors had to be installed. They were built also at many places over the globe, in the United States, in Europe, but also in China and in Japan. Maybe one other thing, last thing of the technicalities, is that there is a lot of cables and pipes in order to get out all the information from the collisions, there are about more than 50,000 cables and pipes which have been installed. And you can see here, of course, some detailed pictures of that kind of work. Okay, so finally, everything was ready in summer 2008, and the technicians and engineers were just putting the last piece of the vacuum pipe where, well, from the LHC collider. So these are end caps. This is the central part of the detector. Again, the collisions will be something like about 8 meters inside from this side here. And as you can imagine, this was a quite spectacular assembly, and there were many important visitors which came to this place to see it. Of course, England, Peter Higgs, Steven Weinberg, really the father of the standard model. Of course, Peter Higgs and François Englet, the fathers of the prediction for the Higgs boson. Let me just mention one other aspect, which I have no time really to go into, but there is a lot of data which is produced because there are about 100 million channels of information. So at each collisions, you have information from these elements, and you have to select interesting events, filter them out, what you want to keep on computer farms, and then analyze them. And this is done by something which is called the Worldwide LHC Computing Grid, which has kind of many huge computer centers all over the globe. Maybe it's one here, something like 12 tier 0 centers, 12 tier 1 centers, and where the data is distributed and then processed, and many tier 2 centers where the physicists are working and making the analysis. Now, not everything always went completely smoothly with the LHC. Just to say that, remember I said in summer 2008 we were ready essentially. So the first tests were made in September 2008, and then there was an incident that one of the supraconducting connections between two elements of the machine, two dipoles, somehow was badly soldered. This joint failed. It made electrical arc and punctured the cooling line, which the magnets, as I said, they work at 1.9 degree Kelvin. So when the helium is warming up, it expands a factor of 10 to the 3. And so it was like a bomb. Quite a lot of these elements were destroyed, and it took about 15 months to repair this. So when everything was back, then in November 2009, people were very worried. What will be happening now? Hopefully it works this time. And indeed, it did work. Everybody was happy. And what people were seeing were the first collisions, which happened actually in 2009, November 2009, of particles here at that time just at the injection energy. So was 900 GeV, the center of mass energy. And the real high energy operation with beams at 3.5 TeV, 3,500 It happened really end of March 2010, and that was really a very great moment. And by that time, Viola Gianotti was already the leader of the experiment. She was my deputy for a long time, and I was happy that she took over. And we had a toast here for, in particular, all the machine builders. And this is Lynn Evans, who was the machine builder of the LHC. So we were happy at that time. And in the first few years, what is called now Run 1, we collected actually information from about 2 × 10⁻15 collisions. So remember, I said 2 × 10⁻13 collisions, you need to see a detectable Higgs boson. So here we have 2 × 10⁻15. So you could already think that in principle we should have seen it, and indeed we did. Well, it's the challenges really are this very high intensity, which has grown. So this was during these first few years. That here corresponds to the 2 × 10⁻15. And as you can see then, in the years 2015 to 2018, at certain TV, we took even much more data. And with higher intensity beams, that means every time when particles were crossing, bunches of particles, there was not only just one collision, but there were on average something like 30 collision or 35 collision. And you need a very good instrument to pick out the ones you're interested in. For example, here, it just shows you many interactions simultaneously, and the one we were interested here in this particular case is the production of a Z boson, which decays in a mu plus mu minus. The muons are seen here outside in this muon detector. So let me now come to the physics, and I will still take something like maybe 15 minutes or so, or 10, 15 minutes. So the first thing we just saw, looking at this mu plus mu minus, for example, was that, well, we reproduced in a way the history of particle physics over many years. Remember, Z boson was discovered in the early 80s, UA1, UA2, but not just 2, 3 events, as you can see here. There are many, many events, this turns up. There were the upsilons, which were discovered also at Fermilab in the 70s, late 70s. Early 70s were the J psi, which have to do with the C quark, the B quark, and so on. Now, what are the typical events? Well, the hard scattering of proton-proton collisions are producing typically jets of particles. And these are high transverse momentum because it's transverse. The beam is here going into the plane, transverse to this beam line. They are, in order to conserve momentum, of course, there are 2 jets of particles, and the occurrence of these jets are a question. They are governed by the strong interaction. And you see here, well, this is looking into the plane. This is a side view. Again, you see the 2 jets. Or similarly, as I showed you from the Z E plus E minus event, this is a map of the energy distribution spaced by 180 degrees in order to conserve the transverse momentum. So you can measure this with a very high precision up to very, very hard scattering, as we call it. And what one tests is really quantum chromodynamics. So the strong interaction. Again, I will not go into much discussion of that. You see this goes over many orders of magnitude in probability, in cross-section, as we say. And in order to have possibility to compare this really with the theoretical prediction, you would not see it on such a highly logarithmic scale. What one typically does, and we will see this more in the coming things, is that one looks at the ratio between the theory and the data. Well, if the theory is perfect, or the data is perfect, this should be at 1. Of course, the experimental measurements, they have some errors, as you can see here, and the theory has some uncertainties. And you can see that, well, this quantum chromodynamic understanding, the strong force in next to leading order QCD calculation, perturbative QCD calculations, is good to about 10% or so. So there's a lot of physics being done in that way, and that's important to understand. Now, the second thing to understand the detector is really to reproduce again the W and C bosons, but now not just 2, 3, but hundreds of millions are produced at the LHC. So this is a transverse view of a W with a nice electron here, and nothing of high momentum balancing it. So it's a typical electron neutrino decay candidate of a W event. Or this is a Z into mu plus mu minus. Now, this we have now seen already a few times. And you can see now on a logarithmic scale with really a lot of data, the nice resonance peak of the Z decaying into mu plus mu minus. And there is very little background. You can see there's only of the order of 1% or so background on the display. So you can measure these processes with high precision, and that is what one was doing. For example, looking at the cross-section, for example, the cross-section of producing a W, which then decays into a lepton and a neutrino. And you can compare this with the prediction, the theoretical predictions, and there is perfect agreement. Similarly, there is a huge amount of top anti-top quarks which are produced. This is again an event picture. Remember, I said, for example, typically are the B quarks, which then decay, of course, into B hadrons, but they have a finite lifetime. So if you look at the magnifying glass, electronically, of course, then you would see this displaced. But then you can compare these inclusive cross-section measurements with what you expect theoretically, and there is perfect agreement. So many, many other processes have been measured and compared to what one would expect for the standard model. You can see this goes over many orders of magnitude in cross-section. You cannot see it so easily on such a plot. So again, we go to our usual trick that when this time we plot the data over the theory. Last time it was the opposite, but never mind. It should be 1 if the measurement and the theory are correct. And they seem to be correct within the errors. So this is really a big triumph for the standard model. and also proves that the experiments are working the way they should. So, having shown these expected measurements, of course, we were then in a good position to pretend a discovery if we make one. Indeed, we did actually make a discovery and announce it on the 4th of July in 2012 by the project leaders at that time. I mentioned already Fabiola Cianotti and Joe Candela from CMS and Atlas. And everybody was very happy, in particular also Peter Higgs and Francois England when the announcement was made. And indeed, even just a year after, they were awarded with the Nobel Prize. Of course, from the experiments, we were particularly proud because in the citation, it says very clearly that the Nobel Prize was only possible to be awarded because the Atlas and CMS experiment at the LHC have actually found the particle. How does it look like? Well, here are the two easiest way to see the Higgs particle. One when it decays in 2 photons, and one when it decays in 2 Z's, and each Z, for example, in mu plus mu minus. And indeed, what you see is above the normal occurrence of 2 photon events, you see an accumulation of events at about 125 GeV. This is again the parent mass of a particle that would decay into 2 photons. So, you see it already here, and if you subtract the smooth background, you see the peak. Similarly, when you look at the invariant mass of 4 leptons, I mean 2 lepton plus, lepton minus, lepton plus, lepton minus, then again you saw an accumulation of events at 125 GeV. And the same thing independent in the second experiment. And that's very important. You make a measurement independently in 2 experiments. This is the gamma peak again at 125 GeV for the CMS experiment, and here the 4 lepton peak at 125 GeV also for the CMS experiment. So we only showed you at this moment actually 2 relatively rare decays of the Higgs. These are all the different modes where we expect the Higgs to decay, and except for this one, we have actually almost seen all of them by now. But because most of them involve neutrinos, they don't show such a nice mass peak. And it was the ZZ and gamma gamma where one could actually see easily a mass peak. Well, if you look at the end of run 1, as I said, until 2012, we see that actually, again, there's no doubt that we had with many standard deviations, both in Atlas and CMS, seen these gamma gamma and CZ modes, but also some other modes were already very significant. And one could actually ask and make a statistical test of what would be the probability, this is just for Atlas alone, that there was just accidental fluctuations of the background that we see a peak. Now, this probability is very, very small. It was 10 to the minus 23. So I guess you can really be sure that beyond any doubt, this was a new particle. And furthermore, it was also seen, of course, independently by. Now, just to let you know, this particle is still there, and now in the run 2 data, 2015 to 2018, you see much cleaner peaks, no doubt. This is, for example, in the 4-lepton or in the 2-photon cases. And I just flashed to you some of the other modes. You see time has gone, so I don't want to be long here. There's also a clear signal, but less pronounced, less sharp because of neutrinos involved. When looking at the Higgs decaying into 2 Ws, each one, for example, in the electron and the neutrino, the mu and the neutrino. So as you don't measure the neutrino, obviously the mass peak becomes much less sharp. Similarly, for example, in the decay in quarks, this is very difficult to find. But there is also a clear accumulation again at 125 G. Okay, so that's the Higgs. Now let me just say that the LHC, of course, is very much motivated also to look at physics beyond the standard model, because we know that the standard model is not the whole story. It does not tell us, for example, what is dark matter, does not tell us why do we only observe matter and where is the antimatter in the universe and things like that. So one of the most promising and still most promising theory is that the dark matter in the universe actually is due to supersymmetric particles, in particular the lightest supersymmetric particle, which was produced in just 10 to the 11 seconds or so, minus 11 seconds after the Big Bang, and we can't see it anymore, except that it interacts gravitationally. And there must be more matter gravitationally acting than what we see is known since a long time, since the 1930s, by Zwicky, Lundmark, or also by Vera Rubin in the 70s, by observing the dynamics of clusters of galaxies or the dynamics of star motions in spiral galaxy. So there must be something, and one of these things could actually be if there would be supersymmetric particles produced, and the LHC might have enough energy to produce them. The way we would see them is that, again, we would have produced particles we don't see in the detector, like the neutrino, but in excess of the neutrino. So we have missing transverse energy, or some variable constructed of it from the standard model due to the neutrinos. And if we would find more of it at some moment in some processes, this could be a hint for supersymmetry. And so there are many, many studies being done like that. Well, supersymmetry can calculate what would be the cross-section, the probability to produce it, and no surprise, of course, the highest cross-section would be the strongly interacting one, like the supersymmetric partners of the gluino or the quarks, and the cross-section are much lower for the electroweakly produced particle. Now, there's no time to explain, but we haven't found any, but made many limits, and we can exclude that, for example, the supersymmetric partners of quarks or of gluinos are lighter than 1 to 2 TeV, so they must be very heavy if they exist. And hence, one is already thinking a future collider. There could also be new interactions, which would mean eventually new heavy particles which are like the W or the Z. One could, for example, see some events, very high mass events of mu plus, mu minus, or E plus, E minus. And we have looked at that up to several TeV in mass, and we don't see any at this moment. That is what you would expect if you would have such a Z prime, for example, at 2, 3, 4, or 5 TeV mass. But we just see a tail of the continuum production of such a. It could also be that there are, for example, exotic particles, very high mass particles which decay in two jets. And we have sometimes two jet masses of up to 8 TeV. And again, we have not really found anything except just the tail of the distribution. So we can exclude, for example, excited quarks up to something like 6 TeV. And many such studies are very much motivated by exotic ideas about physics beyond the standard model. For example, as formulated by Lisa Randall and Raman Sudrum, very famous predictions that there could be extra dimensions, which would mean that one would actually see such random Randall syndrome resonances. And we have many such studies which are being done for things like extra dimension, heavy gauge bosons, for example, heavy quarks, or what is called here leptoquarks. Maybe there are, or there could be also some substructure to the quark. So there's a lot of investigation into the unknown. And these investigations will go on still for a long time, because the LHC so far has only produced about 3% maybe of the data, which we would expect, 3 to 5%. And it's being upgraded for delivering even higher intensity. Also that the instruments, the detector, are being upgraded for being able to cope with even much higher intensities. So we expect still a factor of 20 or so until the end of the LHC lifetime, which is maybe sometimes in 2035 or so. Okay, that brings me to the end. I think I can really say that the Atlas experiment, but of course similarly the CMS experiment and the LHC, its operation has really been a rewarding journey for thousands of colleagues. And the journey into new physics territory with the LHC, as I said, has been a fantastic adventure, and also a nice continuation of the tradition of exploring the high energy frontier with hadron colliders. Therefore, that's why I'm very much like to promote also a collider for the second part of this century, which one talks about, which would increase the energies up to 100 TeV or so. Well, there is still a lot of physics to come with the LHC, and ambitious detector upgrades are ongoing. So that's all. There are some suggested readings possible. Thank you very much.
Thank you for your time, sir. Some of the students have a few questions for you. So we have two questions. So the first one is, hello? Yeah, sir, am I
Yes?
audible? Okay, so the first
Yeah.
question is, hello?
Yeah, I hear you.
Yeah, so I'll be asking you a question written by some of the attendees. So please just answer it, okay? So the first question is, the most exciting aspect of the Atlas physics program is our ability to explore and discover new phenomena beyond existing theoretical predictions, the search for the unknown. So how do fundamental particles acquire mass? Why do they have different masses?
Sorry, I have not understood your question.
So you can read it on the chat box.
Yeah, okay, I have to go, let me see, I have to stop, do this, I guess. How do I do this?
Yeah,
so
you can see it on the chat box. So there is a question by Rahul. Chat box. So the green one, the third icon. Next to time. Next to time. Next to 3:48 p.m.
3:48 p.m. This one?
No. Left to left. Yeah, that one.
Yeah. Okay.
So the third one, the question by Rahul Halde.
Why do they have different masses? Okay. So, well, that's of course the exactly the idea of the Higgs, the broad-angled Higgs mechanism, because what they proposed is that everywhere in space, in vacuum, there is a field which is the Higgs field, as it is called sometimes, and particles actually interact with this field. Those who interact only very weakly, like the electron, it acquires a very small mass, whereas particles which interact very strongly, like the top quark, they acquire a high mass. So it's an effect of the strength of interaction of the Higgs boson with these fundamental particles. That's why also the Higgs likes to decay and couple stronger to heavy particles. So the probability that the Higgs decays into, for example, the tau lepton is much bigger than that it decays into the mu lepton or even the electron lepton. So it's a question of this coupling. Now, why is the coupling like that? This is a property of nature. I mean, it explains how it comes about, but why it is like that, this is not explained in a way. Now, that's all I can say to this. What is also maybe interesting to say is that actually the Higgs boson can also interact with itself. This is called the self-coupling. So one of the prediction of the standard model is the strength the Higgs boson would couple to its siblings, so to speak, and but this only can be seen at really very, very high energy. That would be one of the main motivations also for going yet to a higher energy collider. We might just see a little hint at the end of the LHC when we have enough data, but the real measurement would only be possible at the 100 TeV collider. Okay.
So we have another question by Ankur. Last one. Can there be any possibility? That one.
Let me see if I
It is below that. Yeah, the last one.
Yeah.
Yeah, that one.
Can there be any possibility of too much of energy use? No, I don't think there is a there's a direct link. However, there is a lot of the technology which is developed for hadron colliders, or developed, for example, for the LHC, can actually be used in commercial, if you can call it, or societal application. Let me give you one example. It would be very good if one could transport energy, electrical energy, over long distances with little loss. Well, that makes you sound a bell immediately. You would like to think of supraconducting cables to transport current over long distances. For example, you would have solar cells in the Sahara, and you could transport it to the north of Germany also. Now, of course, normal supraconductor, that would be not very economic, because you would have to cool it down to very low temperature. So this will cost you a lot of money to cool it down. But for the LHC, one has worked on finding, or for the future accelerators, finding supraconductor which are, one calls them room temperature supraconductors. And that could be, of course, very interesting in the long run, if one could actually make almost lossless transport of electric current over very long distances. One could produce the energy at places where you have plenty, as I said, for example, in a desert, and then transport it somewhere else. So this is maybe a far-fetched, at the moment, utopic idea, but people are actually working on such things. And I would say there are societal applications of the technologies. Another much more down-to-earth example is that a lot of technology is used in ITER. This is a thermonuclear reactor, well, still research reactor, which is being built in the south of France. And many of the engineers, magnet engineers, supraconducting magnet engineers who have worked on the LHC or even on Atlas, on the Atlas magnet, they are actually now working on this project, using the know-how in this particular case.
Okay, sir. So that brings us to the end of the lecture. So thank you for your time.
Thank you.
Yeah, yes, sir.
You also sent me a few questions. Should I briefly address them?
Yeah, sure. You can. I thought you missed them. That is why I didn't talk.
No, I have seen them.
Sure.
Okay. So if you have time, I can. So the first one, of course, this is a personal question. Do you believe in the existence of God? I think I'm not want to talk too much about my person, I certainly admire nature, and I hope this is enough of an answer for that one. What then? The second question you wrote, well, what is the difference between the W and Z boson? Well, I have mentioned that the W is the charged variety of the electroweak force carrier, where the Z boson is the neutral one. So that's the answer there. Then there was a question, why not all bosons can be coupled? I'm not sure I understood really the question, but indeed, in first order in the standard model, the bosons are forbidden to couple among themselves if there are only neutral bosons involved. So you will not have a coupling from Z to Z, or ZZ to photon, or Z photon photon, or photon photon photon. I mean, this is just because the quantum numbers, they all have to be obeyed, and this would violate what is called the gauge invariance. So that is not possible. But of course, there could be more complicated ways of coupling. This is only forbidden in the what is called in the lowest order, but then there are more complicated ways where there are intermediate pairs, for example, of a top quark pair which is produced, or things like that, and then they could couple, but that is much rare. Then there is a question, can we take an internship at Cern? The answer is yes. It's of course not so easy, but there are possibilities, and in fact, there are something like summer students, also for non-CERN member states, which sometimes are also Indian students are allowed to do that, of course. And then there is something which is maybe also interesting, and I point you again to my friend Ashana Sharma. She sometimes has students, organizes student visits. There are sometimes students from Indian high schools, or maybe also universities, which come for a week to Cern. So again, that will be somebody to contact for that. Then there was one more question. What are the necessary qualities to be a physicist? Well, of course, one has, I think it's good if one has a very solid education in mathematics, and and then one has to really be enthusiastic and want to do it. It's not always the easy job, but it's also fantastic to look at some of the big question. And then maybe the last one, which I can address, is what's the current big problems of physics that all theoretical physicists are trying to solve? Well, or experimentalists, could one also say. Well, I mentioned one, which is whether there's no quantum field theory for gravitation, so that would be a very big question to solve. Then to understand maybe more also the connection of particle physics and of gravitation in general. For example, it's a very interesting field, certainly, is all these observations of gravitational waves and so on. So these are big things. Then, of course, what nobody understands is the question of why do we see only matter and where is the antimatter in the universe? And what is really dark matter? I mean, there are many ideas. Of course, as a particle physicist, I think it could be a particle which we have not yet discovered, but there could be maybe other ideas. So these are typical type of big questions. Then nobody really knows why there are three families of matter particles. Why three? No? Things like that. So there are many questions, many challenges. Okay, so maybe I leave it at that. Any more?
No, sir, I think this will be all.
Okay.
Okay, then. Sure. Thank you for your time, sir. Yes, sir.
Thank you very much for listening. So,
okay, sure.
all the luck for your studies, and I hope you, Sanket, you have received or downloaded my talk. If somebody wants to have a look at it, they would be very, very welcome if you can make it available that they could look at it.
Yeah, sure, sir. I'll circulate it among all the attendees. I'll surely circulate it.
Okay. And there, people also have my email address. Eventually, I could also answer a question by email.
Okay, sir. I'll also circulate that. Thank you for your time, sir.
It was a pleasure. Bye-bye.
Bye, sir. Have a nice day.
Thank you, sir.